And so we can kind of speed up for the second one. And then we'll take some time to make sure we understand quantum commutation. And then I hope we start getting to microstates today, which are a little confusing to start with, but if you practice them, they get better and better. And so I'm also going to start teaching you about atomic term symbols. And these are things when we get to them, these are things you'll see in like journal articles, all that good stuff. And once you understand them, you'll be able to look at that and go, oh, okay, so this one has, so that molecule has an angular momentum of and it's a triplet. And it tells you about the electronic structure and the angular momentum, which all ends up playing into like reactivity.
Okay.
We start with the term symbols for just like atoms.
Sure.
So it's like, what is the term symbol for a D2 count for like a D2 metal, stuff like that. Okay, so we've done the Lx times Ly. I have expanded slide. I'm just giving myself clean room. Now we're looking at the and some of this stuff. It's funny. I'm having to remember because I haven't done this for 6 years.
Yeah.
And I was working on microstates last night, and because there was a certain kind of electronic configuration where your atom is both a singlet and a triplet. It just depends on the quantum state. But and I look and the whole night just like reading through and doing the derivations and looking at the quantum numbers and figuring out the term symbols. And after 6 years looking at some going like, what the hell is that?
I remember this.
But
Yeah.
And then I looked up, I go, oh crap, it's 2 a.m. Okay.
Chemistry is fun.
So just like the last time, I should probably give myself a little more room in there so it's not all center. Okay, now we're just going to reverse this internal part. And what we're doing now is also going to set you up to be ahead of the curve for PChem. So that's also a nice thing.
I'm excited for PChem.
I like to include things like this. That way, when you see it in PChem, it's not the first time you've seen it, or you're already used to how some of the math works. So you can just kind of dive right in. Plus the textbook I've picked. And I'll show you the textbook we're going to use. I use one. It's actually not to be sacrilegious, but it's been called the Bible of Physical Chemistry. And it's the Donald McQuarrie textbook. And the reason I like it is, how some textbooks, they show you math, but then they skip steps. This one skips nothing.
Nice. I like that.
It does. It's like you go here, now here, now here, now here.
That's good. That's good.
And so it's super easy. Like for some people, they couldn't read it.
Sure.
But once you understand what's being said, it's the easiest step-by-step process to follow.
I'm excited for PChem. I'll have a light semester, and also I'll have like linear algebra under my belt. Then
I think you're going to enjoy linear algebra, especially now that you know that matrices are actually multidimensional maps of a space.
It's cool. I've seen them in action.
Yeah, and so it's not just like this box of numbers, but if you try to imagine like these numbers spacing out multidimensionally, they're actually defining the different different dimensions in that space.
Yeah, they mean something actually.
Wait till you get to Hilbert spaces.
Hilbert spaces.
Because particles live in Hilbert spaces or n by n dimensional spaces. Okay. What do you think n by n means?
N by n. Gosh, I really don't know.
Particles can achieve, at least the math says, almost any dimensionality to fulfill their purposes. So it's like you have 2 electrons trying to do something, and they're like, this XYZ thing's not working for me. Now it's working. Wait, why did it start working? because I'm now in 37 dimensions.
Oh, cool.
But why? I don't know.
I like
Because
that.
I'm an electron.
I can do it.
So, all right, okay, so let's look at this. Let's do this. Let's foil that inside part again. Okay, so now, just like last time, and some people have a hard time with the fact that particles can just end up in hyperdimensionality. I'm like, well, look at quantum entanglement.
Hmm.
Do you know? Have you looked at that or understand how like
I
why it's weird?
wouldn't say I understand it, but I've heard of it.
So, like, imagine you have two particles that are entangled. Okay, they can transfer information instantaneously. Even if those particles were on opposite ends of the galaxy, 100,000 light years apart, they would transmit information instantaneously. Time and space don't matter.
That's cool.
So they're obviously communicating through a much higher dimensional reality. Where we understand time and space, and it would take us, billions of years to get across the galaxy. Particles can talk to each other across the galaxy instantly.
Thing.
It also freaks people out when an experiment that was done that showed that electrons actually know when they're being observed.
Oh, right. That was fun. Man, physics is so cool.
Yeah, well, and I know that I ascribe like human processes to the particle. It's not knowing like we know, or heck, I actually have no idea. But it's not like each electron is a sentient being, but it's
Sure.
just
It has some influence somehow.
yeah, but observed, but their behavior changes when they're
That's it.
observed. And that's called wave function collapse. And it's a unique phenomenon, but it's like quantum mechanics tells you that every single event that's going to occur every micro differential second from now has quantum possibilities.
It's all
It's not-
statistics.
And it's not until you enter into that next moment and you either make a decision or you observe that moment or that it collapses to a single value.
Hmm. Hmm.
And so then the further out you go in time, the more those possibilities spider web, and to the point where, like a year down the road, you have a very large number, but still finite set of quantum possibilities for which universe you'll be living in. And then quantum mechanics says that the you right now that decided not to take a drink from your can, that's you, but then there's another you that did decide to do that, and there's now splinter universes.
Right.
So every second you're creating splinter universes. Thank you, Thanos.
Yeah. Well,
So it's just it's a lot of fun. You're going, wait, what does that mean? Okay, so let's look at this first one here. Okay, so now again we're using our chain rule. So we're going to have z dy dx dgz. Yeah, I hit the record. And then we have the yz, and the derivative goes inside and does the dx dz d. And of course, we have dy dx. That becomes 0, that term does. And so this first term will equal yz. Okay, and now we're going to do the other three terms. All right. And the reason I like to do full derivations in class is when you do these processes multiple times, you start to like see the pieces more clearly.
Yeah.
Instead of just looking like a big jumble. ZDX gives us 0.
No, I feel like in physics, like, I feel like people know what they're talking about. Like, they don't want to answer the question, but a lot of people know the answer. I don't know.
Yeah, I'm trying to figure that out. I don't know. I'm getting to the point where I'm like, I'm kind of like, should I just stop asking questions? Because it's kind of like a rule here for students. It's like, yeah, I'm just going to sit here and stare until the professor moves on. So I think next year I'm going to start this policy where it's like, I'm going to wait till someone answers. And here's the thing, we were going to get through this much material today. If you guys just sit and stare at me, I'll sit and stare at you. And then tomorrow we're just going to move on to the next set of material and you'll be responsible for this on your own. I wonder, because here's the thing, I think young people have a stronger will to not answer than I have to wait.
Probably,
So,
yeah.
I think they can outweigh me on that one. You doubt my powers of not participating. So when you were working through this on your own, are we doing good so far?
Oh, I did not work through this.
Oh.
I'm sorry, I forgot. I thought about it and then I was like, I didn't. I like stayed up late too last night. I probably should have, but I was reading the textbook, so I did something related to this class.
Yeah. Well, plus you have your Embry research.
That's true. I have not done too much with that yet. I don't think my person in Lincoln knows how the program works. I think I'm one of the first students that they've had at least. So it's kind of like
That might be true. It's like me learning research here with students. I think I'm going to get to the point where I might start telling them, here's the projects I have. You get to work with one. Because my machine only has so much room in it and no one listens to me when I say I need small molecules. Small. Okay, so then our last term. Might also, like, I'll help them through it. Good, but just to give them an idea, like future research students, of what the machine is doing, be like, before you start doing research in here, you have to derive the non-zero elements of the Hessian matrix for lithium hydride. It's a simple diatomic molecule. And it's like, and you have to use the harmonic oscillator approximation, just give them the easiest ones.
Sure.
Okay. And then have them do that. And, someone who's never done it before is going to have a hard time with it.
Sure.
But it's like, okay, now imagine that was for the few electrons in lithium hydride. Okay. The few valence electrons, which was 2. Okay. Now, well, it's also the atoms because it also includes vibrations, but whatever. It's like, now you've tried to give me a molecule with 1,000 atoms.
Yeah.
What do you think the computer's doing right now? That's why it's taking so long. Here's our one that's compound 0. All right. And so this in the end will give us X, E, Y plus XZ. And if you look up partial derivatives, there are actually some more symbol more like this, but I don't draw that well. So if you see that, it's like same symbol, It's just the curvy D. All right, so now we have all our pieces, so our just put this all together. Somebody on the room. Not mad, kind of jealous. All right, so now we need to put everything together because you remember our commutator was Lx Ly minus Ly Lx. And what that's going to look like is they're both going to have an I squared H bar squared, so I can pull that out front. All right, so when I put these all together, if I you remember, you need your terms from the Lx Ly, we're going to get Y. This is going to be a long one. Okay, that takes care of our terms from Lx Ly. Now we're going to take all these terms from Ly and Lx and subtract them. That's going to give me minus, well, let's make sure I put it in. Minus YZ basically going to change all the signs on those terms in Ly, Lx. You're about to see what quantum mechanics loves to do. You do a bunch of work. Quantum mechanics does this, and statistical thermodynamics does this a lot. You will do a crap ton of work only for, let's see, YZ minus YZ minus XY plus XY minus Z squared plus Z squared plus XZ. No, I have it. Oh, yeah. Minus XZ. Yeah, you do a crap ton of work for most of it to reduce to zero. That's why in quantum mechanics textbooks, you will see terms like this would say terms involving Y and X, everything, and then other terms. Like they'll just put a bracket says other terms because it's like they're going to go away. I don't know. Okay, so what I end up with, now let's space out the IH bar. This is why I didn't turn I squared into -1. And let's look at what we have left. Y d dx minus x d dy. Now what I can do is I'm going to pull one of those IH bars inside and Well, I'm gonna multiply by a -1 and pull that inside, okay? So that is going to become I H bar negative I H bar, and then multiplying by -1 now reverses these terms. Look back in your notes. What did we just find inside those brackets?
What did we just find inside
Uh-huh.
of it? That really looks like just L2.
Not L2,
That's LZ, sorry.
LZ.
Oops.
Yep. So what we found, well, and it's a factor of I H bar LZ. So couple things have happened here. So let's look at our commutator again. So first off, Lx and Ly working together are not well behaved. So, and what quantum mechanics has just told you, you sat down today and said, I want to study in particular the X and Y dimensions of angular momentum. And quantum mechanics said, here's LZ. He said, great, I'm looking at Lx and Ly. Yeah, you're looking at LZ.
Oh.
No, I'm looking at Lx, Ly. Nope, LZ. But how am I studying those two? But I got the one that's orthogonal to both of them. Because you did.
Yeah.
This is the stuff quantum mechanics does. You're trying to study these two dimensions, but quantum mechanics gives you the orthogonal dimension. Nope, you're not studying what you thought you were studying.
Yeah,
well, why? So also remember so like you can't know the LX LY dimensions simultaneously. That's what the commutator tells you. To know two values simultaneously, the commutator has to equal 0. And so then by extension, because we're not going to do that 2 more times, we get, as you would expect, Ly, Lz equals I H bar Lx, and then Lz Lx is I H bar Ly. So we have these commutation relations. Now we're going to start building some new definitions. We are going to say because these are other derivations we could do, but after a while you'll be able to do these on your own. Which that we would expect just from vector mechanics. And also now the well-behaved systems when L squared commutes with Lx, Ly, Lz, you get zeros. Let's and so remember we're looking for our z direction of behavior in that direction. So let's look at L squared commuting with Lz. Okay, so this is going to then expand into Lx squared, Ly squared, Lz squared, commuting with Lz. We can expand this into three different commutations. No, not Ly. C. Okay. And supposedly this whole thing equals 0. Okay. So let's start with Lz squared Lz. That one's the easy one. All right. Lz squared Lz minus Lz squared. Okay. And believe it or not, the way operators work. Now okay, you remember operators, we can't just simply flip them and have that be okay, because we don't know. In this case we can, but we don't automatically know that. But the way these work, we end up with Lz cubed minus Lz cubed, which is very obviously 0. So that means we did this one, and that one's 0. Now let's look at that one as a whole. So those are the two parts we're breaking it into. So I'm going to do Lx squared Lz first. By the time we're done, you're going to have angular momentum symbols all over the place. All right. So Lx squared Lz minus Lz Lx squared. Okay. Now, that means that we can also expand this to Lx Lz minus Lz Lx Lx. Now, here you see one of the commutators we worked on, Lx Lz minus Lz Lx. Here's the problem. I can't just factor out an Lx because on the first term, it's in the front. On the second term, it's in the back. And we can't just flip them around like that. So we do what physicists do, and mathematicians, it makes their head explode. We go, well, so we're just going to add 0 in the middle. Like, what do you mean add 0 in the middle? What I mean is, so then I'm going to do minus Lx Lz Lx plus Lx Lz C 0 in my last term. Because look now. So these first two on the left, I can pull this and Lx out from the front of both of them. And then I'll have Lx Lz minus Lz Lx. And then the second one, I'm gonna take that LX off the back, pull it out. Great. Now I have commutators. And remember that LZ, okay, so we have LX, oh, sorry. This one, I wrote these backwards. It's supposed to be. There we go. So now one of the ways that commutators do work is we know, and you can go through the math and do this all again, or you can have a little faith. Because you're more than welcome to prove this. But we know that what we derived was LZ-LX, not LX-LZ. Okay. So, but we get IH bar LY. What do you think LX-LZ becomes?
Is it just negative?
Yep.
Whoa.
All right. So that means we now have LX negative IH bar LY plus negative IH bar LY LX. We're going to multiply through. And then this doesn't actually give us a commutator because watch, if I pull out the I negative IH bar, get LX LY plus LY LX. Kind of looks like a commutator, but it's not. Okay. Now that whole thing is our LX squared LZ squared. All right. So this ends up equaling this. Okay. Now I want to do this again for the LY squared LZ. So you get the hang of that zero in the middle.
Okay.
So again, you saw that. So if you look right here, that's just zero. So I want you to get the hang of what to look for, because again, I needed something where I could factor out that LX operator on the front of two different terms and still end up with a commutator. And then I needed some, so then on the other side, it gives me something where I could factor it out on the back and still have the commutator. Okay, now LY squared LZ. And I want to do this also because, like you saw, we did LZ LX and we got LX LY. Okay. So now we're doing LY LZ. You might we're still gonna get LX, LY. It's just, it's not intuitive. Okay. Squared. Okay, so LY, LY, LZ. All right. Now, okay. I'm gonna write the first term. Can you give me two terms that will add to zero that will facilitate this, the factoring?
Do you want the, okay, like,
So just like we did with the LX squared LZ,
you want positive and negative LX,
not LX.
LY, LZ, LY?
There you go.
Okay.
So the first one is our negative one. And our positive one. Okay. And then we have our last term. And we do our factoring. Alrighty, we see our commutators. We plug in what our commutators equal. And then we end up with, well, we would multiply the LYs in like we did last time, but inevitably we end up with IH bar. Again, looks like a commutator, but it's not, because it has that positive in the middle. And so again, this ends up equaling this. Now you remember that I'll come back down in a second. You remember we broke this initial L squared LZ into two separate parts. We proved that LZ squared LZ is zero. So now we found the LX squared LZ and the, well, that's supposed to be LY squared LZ. Why I wrote X, but you know.
So then they're just opposites of each other, they just equal zero?
Ah, there you go. So now, if we put in this term, you're going to get negative IH bar. But see, it's not intuitive that you ended up with the exact same factor twice, just one's negative, one's positive. And that's one of the things that gets a lot of students about quantum mechanics, is they'll make assumptions like, oh, well, If this one comes out like this, then the other one that's like a factor of another dimension will come out like this. But you can't, with quantum math, you can't assume that. You got to work it out, make sure.
It's not intuitive at all.
Not most of the time. And like you stated, you go all the way back to the birth of quantum mechanics, which started with Boltzmann statistics, the statistical mechanics. Yeah, quantum mechanics started out in statistical math. So now we know for a fact that LZ is very well behaved with L squared.
Well behaved just means we can like predict it.
Yep.
Okay.
We can have strong predictions along the Z axis.
Okay.
This is something that will make more sense when I show you the step operators. So it's like, oh, that's why I can focus on those. Okay. So, and that's what I'm going to show you next. So, because your step operators are only built off of X and Y. Again, another derivation we could do. We just don't need to go that tangent right now. So remember, your step operators, you have a wave function, you have a quantum system. Your step operator is a mathematical process that will actually mutate the wave function into a higher or lower quantum state. Okay. And so what it does is it gives you a real physical reality just at a different quantum level. And so we, over the years, operators were found that will do this mathematically. Okay. So, and one of them, let's just do both of them. Step operators. Okay, so
And the plus just means we're going up.
yep, stepping up. L minus. Those are your step operators for your angular momentum. Now, what I love is in my quantum mechanics textbook in college, the Griffiths textbooks are absolutely fantastic if you ever want to get some just to read and to learn. Griffiths, he does electrodynamics and quantum mechanics, but the way he writes, it's real friendly to just work through the textbook. But in his textbook, he had a picture of a ladder with a cat just climbing the ladder.
I like that.
Okay, so these are our step operators. All right. Mhm. Okay, so let's start with doing a combination here. We'll set this up, and then if you get a chance to take a look at it, because this one is really just a simple FOIL method, but then you have to apply some identities. You have run out of time. And when you're and if you're looking at this, this is the time when you can remember, oh, it's not a hat, it's just I squared equals -1. Because you remember what I is, right?
Right, it's the imaginary number.
Yep, it's the square root of -1, so. So we'll finish this up next, on Monday, we'll get it to, microstates. And then we will just continue slogging through this chapter next week. And then over your last week and a half, we'll, like I said, we'll dive into organometallics.
Sounds good. Yay.